Have you ever stopped to think about how some of the simplest, tiniest computer programs can churn out the most unbelievably complex results? Well, today we are diving headfirst into a really fascinating puzzle, right from the edge of computation. We're going to figure out why some programs don't just stop, they get stuck forever.
Come on, you've seen it, right? The spinning wheel of death, that program on your computer that just freezes up. And we always just assume, oh, it's a bug or some kind of mistake. But what if I told you that for a whole class of programs, getting stuck isn't an accident at all? What if it's a fundamental law of how they work? That's the exact mystery we are unpacking today. Okay, so to get to the bottom of this, we've got to visit the scene of the crime. And that scene is a kind of strange world known as the Busy Beaver game. It's this place where computer scientists and mathematicians build these tiny little programs and then just sit back and watch what they do. Now here's where it gets really wild. They started noticing a pattern. A few of these little programs, the so-called Busy Beavers, are just insanely productive. I mean, they run for an unbelievable number of steps, and then somehow they actually manage to halt. But the vast majority of them, they just don't. They get stuck in these endless, repetitive cycles. So what's the deal? What's the invisible rule that's forcing most of these programs into a loop while just a handful manage to escape? To solve this, we're going to have to put on our detective hats. See, if a program is destined to get trapped, the clue has to be hidden somewhere in what it's doing from one split second to the next. What we need is a way to take a perfect snapshot of the program at any given instant. At its core, the kind of simple machine we're talking about here, what's called a Turing machine, is incredibly predictable. I mean, at every single step, it does just these four things. It reads what's there, it writes something new, it moves one way or the other, and it changes its internal mood or state. That is literally it. It's a completely deterministic system, no surprises. So if we want to capture absolutely everything about that machine in a single moment, we need what's called a configuration. You can think of it like a perfect fingerprint. It's got the machine's state, exactly where its little head is pointing, and every single 0 and 1 written on that tape. It is the whole story, all in one shot. And right here, this is where the mystery really starts to unravel. See, even though a program could theoretically run forever, the number of unique fingerprints it can have within the space it's already explored is not infinite. Nope, there is a hard limit, a finite number of possibilities. Let's call this its configuration budget. So what exactly goes into this budget? Well, it's basically three key ingredients. First up, you've got the machine's internal state, its mood, and a program only has a fixed number of those. We'll just call it N. Second is the head's position on the tape, but only within the range it's traveled so far. And third, the unique pattern of ones and zeros it has actually written down. As you can see, each of these components has a limited, totally countable number of possibilities. Now, when you multiply all those possibilities together, the number of states times the head positions times the tape patterns, you get the total configuration budget. And look, this number can be absolutely astronomical, just huge. But the most important thing to remember is that it's finite. There isn't an endless supply of new snapshots, there is a limit. Okay, so now we have all of the clues. We've got a program that chugs along one step at a time, and we know it has a finite budget of unique snapshots it can be in. The trap is about to be sprung. Let's frame this with a super simple analogy. On one side, we have our pigeons, and those are just every single step the program takes. One step, one pigeon. On the other side, we have our pigeonholes. That's the limited number of unique snapshots or configurations that are available in its budget. And that leads us to the big, pivotal question. What has to happen if the number of steps, our pigeons, eventually becomes greater than the number of unique snapshots available in its budget, our pigeonholes? The answer comes from this beautifully simple rule of logic called the pigeonhole principle. All it says is that if you have more pigeons than pigeonholes, you're guaranteed that at least one hole must contain more than one pigeon. You just run out of unique spots. There's no way around it. It's a mathematical certainty. And right there, that's the gotcha moment. If a program runs long enough that it completely exhausts its configuration budget, it is forced to repeat a configuration it's already been in before. And remember, the machine is totally deterministic. So the second it re-enters an old configuration, it's going to follow the exact same path it did the first time, and the time after that, and the time after that, trapping it in an infinite loop. Game over. So what does all this mean? Well, this isn't just some clever logic puzzle. It's actually a fundamental law of computation. And the researchers who figured this out, they gave it a brilliant name, the Busy Beaver's Dam. Here's the big idea, and it's a powerful one. Time must be paid for with novelty. A program's runtime is like water building up and up behind a dam. That dam is its configuration budget. So if the program stops creating new and unique snapshots, if it stops exploring new parts of the tape or writing more complex patterns, the water level of time just keeps rising until eventually it has to spill over, forcing a repeat. The program literally traps itself.
So the only way out, the only way for a program to have a really long runtime without getting stuck, is to constantly raise the height of that dam. It is forced to expand its resources. It has to keep pushing into new territory on the tape, or it has to keep writing new, more complex information. It has to keep generating newness just to survive. And that leaves us with a final, really powerful thought. This whole thing isn't just about tiny theoretical programs. This is a fundamental law that says computation demands space. It demands novelty. It demands resources. So if even the simplest little programs are constrained by this dam, it really makes you wonder, right? What kind of invisible configuration budgets and hidden logical walls are out there right now, shaping the absolute limits of our most complex software and even the artificial intelligence we use every single day?